Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. We from Group 1 and my name Abdul Rafi Aziz bin Abdul Aziz.
My name is Sadana Balkis binti Abdul Mukmin.
My name is Amira Ridwana binti Hazman.
My name is Azlana binti Baharudin.
And my name is Aryan Shane Askasilaw.
Okay, so today we will present to you guys about our assignment, and we have two parts, which is part A, the mechanism of tensile test, and part B, the mechanism of hardness test, which is we choose after we get the situation. And we can start. Miss Aryan, can you introduce about part A, the mechanism of tensile test?
So, in today's market, the emphasis on durable products for safety and quality, especially in critical structures like skyscrapers and aircrafts, is driving demand. Tensile properties, which are crucial in construction, are assessed through tensile testing, a vital technique in material science. This method involves subjecting a sample to controlled tension to reveal key qualities such as ultimate tensile test, tensile strength, and ductility. Tensile testing serves multiple purposes from materials selection and quality criteria to facilitating comparisons during material development. Moreover, it provides predictive insights into material behavior under diverse loading scenarios. This presentation explores the vital role of testing in shaping a future where durability, safety, and high quality engineering are seamlessly integrated. Now let us move on to its theory. The primary purpose of tensile tests is to determine the mechanical properties of a material under actual tensile forces. These properties include yield strength, which is the stress at which the material begins to deform plastically. Ultimate tensile strength, the maximum stress the material can withstand before failure. Elongating at break, meaning the amount the material stretches before breaking. Reduction in area, the reduction in the cross-sectional area of the specimen at the point of fracture. Modulus of elasticity, a measure of material stiffness. Poisson's ratio, a measure of lateral contraction when a material is stretched. Stress, it is the applied force divided by the original cross-sectional area of the specimen. Stress is measured in pascals or megapascals. Strain, it is the change in length of the specimen divided by its original length. Tensile test helps understand how materials behave when pulled, providing valuable information about their strength and flexibility.
Okay, thank you, Miss Aryan. Next, in this report and assignment, we have the parts and question that we need to explain, which is explain how the tensile test conducted and discuss about the specimen used, justify the relationship between the size, and define tension, stress, engineering stress, through strain and modulus electricity, and the data that we have. So, Miss Amira Ridwana, can you explain?
Okay, so for the first question, we need to explain how the tensile test was conducted. Before the test, a few things must have been done. Firstly, gauge marks were placed on the specimen. Thereafter, the initial length and diameter of both specimens were taken. Then, the specimen was placed into the machine whereby they were tested until fracturing occurred. The diameter and final gauge length were then taken after completion of the test. The tensile test experiments data recorded. The curve will display where the tensile profile until the point where the specimen succumbs to the force and breaks. To measure the stress and strain of the material, the tensile testing machine will be used together with the accompanying software to record the tensile behavior of the specimen. Through the data, an associated deduction can be made about the properties of the material. So for the question 2, we need to discuss about the specimen we use. The material used for tensile test was HDPE, which is high density polyethylene. HDPE plastic is a polyethylene thermoplastic that is made of petroleum. It has high density, high length, high impact resistance, is lightweight, can last for a long time, and resist the weather as well. It is widely used for bottles and containers for foods, drink, personal care products such as shampoo and household products. A tensile specimen is a standardized sample cross section. The sample is dome shaped or also called dog bone shape. The dumbbell dimensions are modulated as a function of the material thickness. Sample cutting is of paramount importance of obtaining accurate and reproducible results. It has two shoulders and a gauge in between two of shoulder. The shoulders are large so they can be ready to be gripped, while the gauge section has a small cross section where therefore the deformation and failure can occur in that area. That is the figure show the tensile specimen. The thickness of the material is 2 mm while the weight is 4 mm. For the next question, we need to justify the relationship between the size of the specimen and the force to be applied. Things change when force are applied to them, but not all items change the same, even if the same force is used. Before looking at what causes this change, there are a few concepts that need to be looked at first. Stress is the amount of forces that is being exerted on an object divided by its cross-sectional area to account for size. Larger objects are able to withstand higher force. By using stress instead of just force, we are able to use the same yield strength for the same material regardless of how large the object actually is.
Okay, thank you, Miss Amira, about the explanation. And we have another 3 questions in part A. So I think Miss Azliana can continue the question.
Thank you, Rafiq, and thank you, Amira. Okay, I will elaborate about the definition of tension stress, engineering strain, true strains, and modulus of elasticity. As shown in the slide, a tension stress is defined as the force per unit area that a material experience when exposed to a pulling or stretching force. It is sometimes referred to as a tensile stress. It is given in megapascals or pascals, which are units of force per unit area. Next is engineering strains. It is a measurement of a material's elongation or distortions in relation to its original length. And it is commonly represented by the symbol of epsilon. It is computed by the dividing the length changed by the initial length. It may be mathematically represented as a formula given, where is the change in the length and is the the bigger L with initials of O is the original length. Then furthermore, the definitions for the definition for true strain, it is represented by is an additional deformation measure that consider the length of a material that change instantly and continuously during deformation. It is frequently applied in circumstances involving significant deformations. The following formula links engineering strains to actual strains. So last but not least, the modulus of elasticity. The modulus of elasticity, also known as a Young modulus, that represented by the symbol alphabet of E, a measure of a material's stiffness within the spectrums of elastic deformations. It characteristic the ratio of stress to the corresponding strain in terms of in terms of mathematical formula. Young modulus is expressed in pascals or gigapascals. Unit is frequently used to describe the elastic properties of materials. Okay, next, for the experimental data, so the tension stress, we need to calculate the tension stress, engineering strain, and true strain, and the modulus of elasticity. So as shown in here, this is one of the assignments that the test that we already did. So here, the data, the dimension, the thickness of the material is 2 mm and the width is 4 mm. And here are some of the calculations by using the formula that given, and also that the theoretically formula and mathematically formulas that are already we learned in our classes. See, okay. Next questions. We need to compare the tensile stress strain graph for a brittle and ductile material. So, as shown here, this at the left side, this stated here is the brittle material graph. It's in a linear, and this one is the strain graph, which is in this particular pictures. So here I'm going to share about the difference between the brittle materials, the brittle material and the material. Brittle materials is normally indicate a stress strain curve with a pointy top accompanied by a way of means of sudden fracture. So the graph indicates the minimums of plastic deformation earlier than the failure. So the fracture is commonly an end result of a cleavage or other brittle fractures mechanism. In the graph, you could see a step forward thrust in a pressure till it reach a maximum value, which is y, the point y. So after which there may be a sudden drop indicating fracture. So brittle substance lack of great plastic deformation, and their failure is abrupt. At least at elastic region, brittle materials indicate elastic deformation on the preliminary phase of the stress strain curve. These sections manifest as the linear behavior, and the material regains its shape after the burden is removed. The stress strain relationship in the course of these sections complies the Hooke's law. So next around, the yield point. The yield point is regarded as the very best stress degree brittle materials can undergo without incurring everlasting deformation. If stress surpasses these thresholds, the materials might not revert to its original form as soon as the weight is relieved. So when the materials, like if have tensions in that materials, it's not like will come back to the shape instantly. So next is the fracture point. In comparison, the fracture points, the F point, in comparisons to ductile material which go through a remarkable plastic deformation, brittle substances come across the fracture point tremendously early in the stress strain curve. This juncture marks the stress at which the material fracture fractures. So last but not least, brittle fracture, a situation after the fracture point. Brittle materials encountered a sudden failure. So a fracture in the brittle material sticks out for its loss of extensive plastic deformation. Resulting fracture surface generally tend to seem easy and clean. So next, I'm going to explain about the ductile material. So while ductile materials go through a massive plastic deformation earlier than failure, the stress strain curve for ductile material display a greater slow growth in stress and indicate a distinct yield factor. For the ductile material, stress strain curve, the graph showing a yield point where the plastic deformation begins, followed by a way of means of strain hardening till eventually necking and failure. So ductile material are characterized via of their ability to deform plastically earlier than rupture. So at point A, the proportional limit, it indicates the stress strain remain directly proportional following their Hooke's law. At point B, which is the elastic limit, the material demonstrate elasticity. The material regain its shape upon removing the external load without any deformations. At yield point, which is point C and D, the stress strain graph nearly horizontal due to a strain hardening. Uh, the curve as okay, the curve ascend because the materials consist of the load, marking the transitions to plastic deformation of a almost everlasting nature. So next, the ultimate tensile stress at point E is the point the maximum stress a material withstand prior to failure. In particular, the specimen would not fail at this juncture, and the curve commences descending thereafter. So lastly, a breaking point at point F, the materials uh, where the materials fail. Necking occur after the ultimate tensile stress. This causes less load bearing capacity and causing a failure. So for the example of the brittle material that are applied to an aircraft, structure is a carbon fiber reinforced polymer, CERP. The part of the structure is a tail plane, horizontal stabilizer. This is because carbon fiber composites, despite being sturdy and lightweight, they are distinctly brittle. They are frequently used in the tailplane of an aircraft, wherein the material excessive power and stiffness are advantageous. However, the shortage of massive plastic deformation makes them extra vulnerable to unexpected fracture. So next, the example of ductile material is aluminium alloy, and the part of aircraft structure that using aluminium alloy is a wing, the wing of the airplanes. This is because aluminium alloys such as 2024 or 7075 are commonly used in the construction of aircraft wings. The ductility of these materials allows the wings to undergo deformation without intermediate failure, which is crucial for the flexibility and safety of the structures. To sum up, in aircraft design, engineers frequently use a combination of materials, selecting each based on its specific properties and the requirements of the particular structure component. For example, wings may have a structure primarily made of ductile materials like aluminium alloys, while other components like a tailplane may utilize the strength to weight ratio of brittle materials like a carbon fiber composites. That's it. Thank you.
Okay, thank you, Miss Azliana, with the detailed explanation. After the test, I want to ask Aryan, what is the conclusion of the part A?
So, to conclude, the tensile test experiment using high density polyethylene and a universal testing test machine helped to determine the value of stress and strain as well as Young's modulus. This allowed the tension stress, engineering strain, true strain, and modulus of elasticity to be calculated. However, the experiment encountered some challenges. Errors cropped up during the measurement of the specimen's dimension, particularly with the use of a vernier caliper. The precision of this tool demands careful attention to ensure accurate readings. Furthermore, the frequent use of the tensile test machine introduced the possibility of slight errors to the data. To address these challenges, a deliberate effort to properly arrange and bind the specimen to the grasp maintained a firm hold at the fixed head, preventing any unintended loosening during the experiment. While challenges were encountered, the experiment provided valuable data for understanding the behavior of high-density polyethylene under tension, with an awareness of the potential sources of errors contributing to more comprehensive interpretation of the results.
Alright, thank you, Arin. So we have done with the part A. So we continue with part B, which is the question give us situation, and we need to choose the test that suitable with the situation, and we have choose the mechanism of hardness test. So Aryan, can you explain us about introduction and theory of hardness test?
Okay. So hardness is a crucial factor for determining how tough and resistant a material is to wear and deformation. It helps assess a material's overall strength and durability for different uses. Hardenability, specifically in steel, measures how easily it can be transformed into a tough structure called martensite during a cooling process called quenching. This property is essential in understanding a steel's ability to handle stress and form martensite during quenching. It's important to note that hardness and hardenability are related but distinct concepts. Hardness gauges a material's resistance to deformation under a load, while hardenability focuses on how well it can be hardened to a certain depth under specific conditions. The Jobini end quench test is a widely used method to measure the hardenability of steel. Notably, the abundance of Jomini data collected on a large scale provides a high level of certainty, making it a convenient and reliable tool for understanding the hardenability of steel plates. This presentation discusses the applicability of hardness testing because of the significant insights it gives to the mechanical characteristics of materials. So, moving on to the theory, the Vickers hardness test is a method based on the elastic plastic deformation of materials under load utilizing a diamond intender. When pressed into the material surface, both elastic and plastic deformation occur. Elastic deformation is reversible, while plastic deformation is permanent. The Vickers hardness number, or VHN, is a dimensionless quantity representing the ratio of applied load to indentation surface area. So the Vicker hardness number is calculated using the formula VHN is equals to 1.8544 F applied force d squared. Importantly, if the load is proportional to the indentation area, the Vickers hardness number, or the VHN, remains independent of the load and indenter size. Conversion tables or empirical equations allow the VHN to be transformed into other hardness scales like Brinell or Rockwell hardness numbers.
Alright, so next we will continue with the question, which is question A, the situation that we give and why we choose hardness test uh, during the situation that have given. So Miss Adriana, can you explain to us?
For this question, the hardness test is a suitable test to evaluating the situation, such as bird strike, drop tools during aircraft maintenance, tarmac debris, kick up by the wheels during the takeoff or landing, and large hailstones. This is due to the fact that these tests are used to determine the hardness of different materials. Depending on the material, small sphere with a higher hardness than the material under test These tests compare hardness based on the application for which the material should be used. For example, if you are looking for the best aluminium for an airplane fuselage, the material you choose should have the highest hardness, not necessarily the hardest, because tenacity should be considered as well.
Okay, thank you, Miss Adriana. So now I will explain to you guys how we conducted the hardness test. First, ground along the specimen to get a flat surface. Second, clamp the sample at the weakness hardness tester. Third, set the load. And next, look through the microscope. You will see two parallel lines. Move the line until both lines are sticking together. And then you press the reset. So I want to show you guys how you look through the microscope. And then next step is turn the indenter to the center or front. Move the specimen up until it touches the sample. Push the start button and leave until the lights are off. Move the stage down and turn the microscope to the center. Look through it and move the stage up until you see diamond shape. Move to do the measurement. Move the line at each of the corners like this, and press read. You will get the value of D1. Turn to the other corners and press read. Take the reading at each 1.5 to 2 mm, at least 15 readings to plot the hardenability curve. And lastly, you need to record all of the reading in a table. So next, we need to define the material that is suitable to apply for the test. So Miss Adriana, can you tell us?
Thank you, Rafi, for briefing how the test is conducted. For this part, workwear testing is the most used method for alloy and metals since it produces results fast. Loops and Vickers tests are useful for coding in material and mounted metallographic components. Brenner testing is commonly applied to large steel buildings, cast iron and aluminium structures. Certain hardness tests may be finished in a couple of seconds with a handheld device. For this test, copper, aluminium, mild steel and hardened steel are all suitable materials.
Thank you, Miss Diana. So next, I will describe the data that can obtain from the test. First, hardness test, we can access material qualities such as strength, ductility, wear resistant. Also, they determine whether a material or material treatment appropriate. And we can also diagonal of a square and the diameter of a circle. Vickers tests differ from Brinell's. Uh, Determine materials resistant to persistent deformation. We also can determine the specified load on the indenter, a specific loading time profile and a specific load duration, and a specific indenter shape when drawing conclusion from hardness test. So after all of the tests that we can conclude, so Miss Arin, can you conclude the test?
So, in conclusion, The Gemini and Quench test stands as the gold standard in the industry for gauging steel hardenability. This crucial property signifies a steel's ability to be quenched and toughened in depth. Hardenability, influenced by alloy composition and prior processing like austenitization temperature, plays a vital role in determining a steel's performance. Understanding steel hardenability becomes imperative in the selection of appropriate alloys and heat treatments for components of varying sizes. This knowledge is key to minimizing thermal stresses and deformation, ensuring that the chosen steel meets the specific requirements of diverse application. Fundamentally, the Gemini test insights into hardenability contribute significantly to inform decision making and making in material selection and heat treatment process within the steel industry.
Uh, Thank you, Miss Aryan, and that's all of our presentation. And thank you. Bye.